Okay, last time, of course, we defined the operations of matrix scalar multiplication and matrix addition. And the key point there, I'm going to, of course, go through an example of doing those operations, but the key point there was that we defined the scalar multiplication of a matrix so that it reflected the scalar multiplication of the underlying map. And we defined the sum of two matrices so that they reflect, so that that operation reflects the representation of the underlying maps, the sum of the underlying maps. So we're going to do more of that today. So keen on emphasizing that. Okay, here we go. So obviously, I just made up an example where we have two maps, and I'm going to consider the H and G and H plus G and all that kind of stuff, and then represent those. Okay, let's get started. All right, so let's see here. I've got to remember what I'm doing here. So H and G map poly 2 to r squared, poly 2 to r squared. Okay, and H does what? H takes a plus bx plus cx squared and gets you to b and a plus c. Whereas G takes the same thing, a plus bx plus cx squared, and gets you to, what does it say? A plus b and minus 2c. A plus b and minus 2c. Okay. Okay, so I've got to figure out here what is h of what is h of 3 plus 2x plus x squared, h of 3 plus 2x plus x squared, so 3, 2, 1. And of course the action of h is to take the coefficient of x and put it on top, and take the constant term and the coefficient of x squared and add them together and put that in as the second component. So 3 and 1 makes 4. G, on the other hand, takes the same thing, 3 plus 2x plus x squared. And G's action is to take the constant term and the coefficient of x, add them together and make that the first component. And then take the negative 2 times the coefficient of x squared and make that the bottom, so minus 2. And then 4h, acting on the same thing, 3 plus 2x plus x squared, just goes to whatever 4 times 2 is 8, and 4 times 4 is 16. And H plus G, acting on the same thing, 3 plus 2x plus x squared, write it halfway between the two because it's a combination of the two maps, and you add 2 plus 5 to get 7, and 4 plus minus 2 to get 2. Okay, so it makes sense to multiply h by 4, it makes sense to add h and g. The second question says represent h with respect to the given bases. So 2, I'm given bases b and d, and b is what here 1 plus x, and 1 plus x squared. Okay, and then d is the standard basis for 2 space. That's terrible. Standard basis for 2 space, which is of course 1, 0, 0, 1. Okay. Okay. So to represent h with respect to b and d, I have to figure out where do the elements of b go, and then represent them with respect to the basis d. So where do the elements of b go? And they go to 0, 1, they go to 1, 1, and they go to 0, 2. And of course, the representation of these three with respect to d is the standard basis, so vectors are represented by themselves. So the representation with respect to d of 0, 1 is 0, 1. The representation with respect to d of 1, 1 is 1, 1. A lot of chicken scratching. And the representation with respect to d of 0, 2 is 0, 2. And when all the smoke clears, when all the blab stops, you're looking at the representation with respect to BD of H is, you just put those three together, 0, 0 as, 0, 1 as the first column, 1, 1 as the second column, and 0, 2 as the third column. So 0, 1 as the first column, 1, 1, and then 0, 2. The representation of G is pretty much the same thing. You figure out what does G send the members of the basis B. So 1 goes to under G, 1 plus x goes to under G, and 1 plus x squared goes to under G. And it is 1, 0, it is 2, 0, and it is 1 minus 2. I have to represent those with respect to D. The representation with respect to D, because D is the standard basis, the representation with respect to D is 1, 0, 2, 0, and 1 minus 2. I'll spare you the agony and just write the representation with respect to B comma D of G is, write them all down, 1, 0, 2, 0, 1 minus 2. Okay, you can write that if you like. You can leave it out if you like, whatever suits you. And then finally, the last part, the sort of point of the question, is represent 4H, representation of 4H with respect to B comma D. 4H is a perfectly good function. I have an example of 4H's action right here. And the representation of 4H is you simply find the representation of H and you multiply it component by component times 4. So 0, 4, let's see if I can do that. 0, 4, 4, 8. That's a perfectly good function. Here I show its action on some input element, some member of the domain, and to get the representation of 4H with respect to the same bases, B and D, you just multiply component by component. And finally, the representation with respect to BD of H plus G. And of course, we would take the matrix for H and the matrix for G, and we'll add them together, component by component. So 0 plus 1 makes 1. 1 plus 2 makes 3. 0 plus 1 makes 1. 1 plus 0 makes 1. 1 plus 0 makes 1. 2 plus minus 2 makes 0. Okay, so the sum of the two matrices is the representation of the sum of the two maps. And again, the idea from last time is that the sum of two matrices is very easy. It's so easy that a person wouldn't ask themselves, why are we doing this? But a person needs to ask themselves, why are we doing this? Because in order to understand what we're talking about today. Okay, so let's turn to what we're talking about today. We're talking about representing a function operation, namely the function operation of composition. We already did the function operation of multiplying by a scalar. We already did the function operation of adding two functions. The function operation we're going to do now is the composition of two functions. So if you have f as a linear function, g is a linear function, and it's legal to compose them, the domains and codomains match up, then how do you represent f composed with g? Okay, so another function operation besides scalar multiplication and addition is composition, and the composition of linear maps is linear. We actually have already seen that, but it's not very hard to show. So I have G composed with H, and I've arranged so that the domains and codomains match up. Specifically, the outputs of H and the inputs of G are the same. So G circle H on a combination is the combination of the G circle H's. And we've done lots of these before, so I won't go through the steps. G circle H on a linear combination is the linear combination of the G circle H's. Now, the way that I developed the theory, the formula for scalar multiplication of a map and the formula for the sum of two functions was I did some example with numbers, and then when you go to say to yourself what should the right definition be, there was just no question. So we're going to do the same thing here. We have two linear functions, f from v to w and g from w to x. So you notice again the W and the W, so it makes sense to take H first and then G. Makes sense to take G circle H. And I made up a matrix representing H and a matrix representing G. You'll notice that they don't share any numbers. So if, when we get further down, if you see like a 3 or a 6 or a 10, you won't say to yourself, which 10 is that again? Oh, and I spelled explanatory wrong. So I'm going to do the composition. That is to say, I'm going to take a vector from V, find h of little v, going to take a vector little v, find h of little v, and then I'll find g of that, g of h of little v, and that will tell me how the two matrices combine. So it's really the most straightforward thing a person would do. If nobody had invented this before and you were sitting in a room thinking to yourself, what do I have to do? This is exactly what you'd do. You take some vector from capital V and represent it with respect to the basis B. It so happens the shape of this matrix is such that the elements of the domain domain is two-dimensional. Elements of the domain are represented by a too tall vector because there's two columns. So I picked a too tall vector just because that's the example that I'm doing. I'm not working with i's and j's. I'm working with actual numbers, just thinking that it makes the whole thing more concrete. And we know how to do this: 3 times v1 plus 1 times v2, and etc. So this is how you figure out h of v, h of little v. And now the next thing I'm going to do is going to take g of this. 8, 7, 11, 9, 10, 12 of this. So here we go. I didn't make it all on that slide. I had to go on the next slide. So here we go. I'm taking g of what was on the previous slide. So 8, 7, 11, 9, 10, 12. And it's a little long. It took a lot to write. It's not actually very hard to figure out. It's 8 times the first, 7 times the second, 11 times the third. Next line, next row, is 9 times the first, 10 times the second, 12 times the third. But it takes a lot to write down. Let's see, what happens? Well, I'm going to gather together all the V1 things and going to gather together all the V2 things. So that's 8 times 3, 7 times 2, 11 times 4, and that's what it says there. To gather together all the V2 things, it's 8 times 1, 7 times 5, and 11 times 6. So there it is. So the V1s are there and the V2s are there. Rewriting that in terms of matrices, there's the 8, 3, the 7, 2, and the 11, 4 that I pulled out of there. That goes there. There's the 8, 1, the 7, 5, the 11, 6. There it is. I just pulled those out and broke this up to express it as a matrix times a vector. But this is the matrix I'm looking for. This is how you compute the composition G circle H on the vector V. So this is how the two starting matrices combine. If you start with, remember here's G and here's H, because in composition you write the thing done first on the right. You put down the thing done first on the right, you put down the thing done second on the left. That's how you do composition. That's the notation. So that's what I did. I put the thing done first on the right and the thing done second on the left. Okay, fair enough. Here's the H matrix. Here's the G matrix. This is capital H. This is capital G. And this is just how they combine. So in the last class, in the last video, when I said this is the way that the parts of a matrix get combined when you want to multiply, when you want to look at the map 4F, and this is the way that the parts of the matrix combine when you want to look at them, represent the map F plus G. Well, this is just how the parts of the matrices combine when you want to look at the composition G circle H. It's just how they combine, that's all. How do they combine? So 8, 7, 11, and 3, 2, 4. So you take the first row and the first column, 8, 7, 11, 3, 2, 4, and you take the dot product. There it is right there. And why do you do such a crazy thing? Because that's just simply how they combine, that's all. 8, 7, 11, 1, 5, 6. So to figure out the thing in row 1, column 2, you take row 1, 8, 7, 11, and column 2, 1, 5, 6, and dot product them. And a person can very sensibly say, when you first see matrix multiplication, that's what we got here, matrix multiplication. A person can very sensibly say, why are you combining them in such a strange way? And the answer is, we're combining them in such a strange way because that's simply how they combine. So the definition is the matrix multiplicative product of the M by R matrix G with the R by N matrix H is the M by N matrix P, where you figure out that component, you figure out the element of row I and column J by taking row I dot product with column J. You take row I of capital G dot product with column J of capital H, and that gives you entry IJ. That's what it says here. The dot product is more clear here, but the row I and the column J is more clear here. So just as an example, just to pick an example here, I just made up some numbers entirely divorced from any consideration of functions. So 316 and 259 by 204, 1 minus 35427. A person notices that these are 3 wide and these are 3 tall. That's necessary. You got to have R, got to be the same as R. So just to pick on one, I'll just pick on, how about if I take 316 and dot product it with 0 minus 32. That's the first row dot producted with the second column. First row, second column will be this fella right here. I think, I could have made a mistake, but I don't think so. 3 times 0, 1 times minus 3, 6 times 2, add them together, gives you a 9. So you take row I, column J, and that gives you the entry for row I and column J in the result. And again, I can't overemphasize that it isn't an arbitrary definition. This definition is just simply the way the letters fall. That's all. When you go back to this slide, that's just simply the way the components fall when you do the composition. When you do H first and then G, the parts just simply combine in this way, and this is a transcription of how the parts combine. Another example. So here I have 3 wide, 3 wide, and 3 wide. Here I have 2 tall. 2 tall. So if the number of columns on the left does not equal the number of rows on the right, then it's not defined. The matrix product is just simply not defined. And it's not defined for the simple reason that it can't make sense as a composition of 2 functions. This has a 3-dimensional domain. I mean, it just doesn't make sense. It just doesn't line up as a composition of 2 functions. Sometimes people ask me something like, well, can I imagine that there's a row of zeros? No, because that doesn't make sense in terms of the domains and codomains of the underlying function. Square matrices of the same size always have the defined product, so that's an especially convenient fact about them. So here I have a 3 by 3 and a 3 by 3, so of course 3 wide and 3 tall. So the fact that these matrices are square means that means that you can combine them, multiplicatively combine them, and that reflects the fact that we can always compose 2 functions from a space to itself. So if H is a function from V to V and G is a function from V to V, then V is 3-dimensional. Then you're just looking at G circle H. Of course, it makes sense because the codomains and domains are all the same. Just to pick on an example, how about if I take the bottom row here, 2, 0, 0, and combine it with the third column, and I'll get bottom row, third column. So 2, 0, 0, dotted with 1, 0, 2. 2 times 1, 0 times 0, 0 times 2. I think I do get the 2. A person might notice that second row has all zeros, so when I take the second row and dot it with the first column, or the second row dotted with the second column, or the second row dotted with the third column, anything you dot with 0, 0, 0 is going to give you zeros, and so a row of zeros will result in a row of zeros. There are some things you can notice about how the parts of these matrices combine with the mechanics of matrix multiplication. We'll talk about that. That's coming up. We'll certainly have a lot to say about that. And then the takeaway here. Of course, when a person does the homework, they're going to be saying to themselves, how do you combine this part and what happened? Oh, I lost a minus sign. I got to go back. But no, and this is not defined. But don't lose track. Don't lose the forest for the trees. the composition of linear maps is represented by the matrix product of the representatives. That is to say, matrix multiplication is a somewhat peculiar definition. You say, so why are you doing this crazy way? And the answer is because it represents the composition of the functions. So if you have some conception of what the functions are, this function rotates and then this function makes 3 bigger, then you can make sense of what happens when you multiply the underlying matrices. Okay, now next time we're going to do more of the same, more practice, but it's certainly time for a person to go away and try some problems. Okay, very good. Okay, bye bye.